Let's get started. Apparently my mic is live. That means it's time to go. I'm not sure I had time at the end of Tuesday's lecture to take questions. So let me just start with that. Anything that's been bothering you since then? Oh, I guess we had the discussion session, but yeah, that's okay.
Yeah, last time you mentioned that there is this situation of the mass gap and the phase transition. And you said that it's not possible to cure this just with perturbative corrections. Why is that?
It seems that
we will have this discontinuity in the derivative, and if we add some corrections, we might make this transition smooth.
And that's what's going to happen, but they can't be perturbative. So this, the discontinuity in the first derivative is already at order 1 over g Newton. And so no correction you can add that's perturbative in g Newton can possibly cure this. Yeah, and that's a general rule. I mean, phase transitions are always smoothed out by non-perturbative corrections. Anything else? Okay, so let me actually start with a general remark that I might have implicitly made, but something Aaron said reminded me of it, which is that I motivated Ryu Takanagi from Bekenstein-Hawking, essentially, and but what we've seen is that I mean, so one of the things that, Aaron said at the beginning of his lecture is that we're interested in black holes not just for their own sake, but because they presumably give clues to how space-time, what's going on with space-time at the quantum level in general. And so this is just an example of that, where Ryu Takanagi essentially can be thought of as a vast generalization of Bekenstein-Hawking. And what it's saying is that Bekenstein-Hawking was this connection between entropy and area, actually, although it was first derived in the context of black holes, actually has nothing to do with black holes. That's just this one special case, because the horizon of a black hole happens to be a minimal surface. Has nothing to do with black holes, has nothing to do with horizons. It's much more general. So if there's a minimal surface crossing this room, then there's an entropy associated to that minimal surface. So I just, that's one reason to be excited about Ryu Takanagi from the point of view of using holography to understand quantum gravity. I mean, the other reason is from the point of view of using holography to understand strongly coupled field theories. And so it's been very fruitful there as well, of course, because it allows you to calculate, which is kind of what I emphasized more at the beginning. Okay, so I want to finish. So what I was doing, in case you don't remember, because it's been a while since we've seen each other, and we've been learning so many interesting things from other lecturers. So what was going on at the end of my last lecture? I was giving a grand tour of applications of Ryu Takanagi in simple situations to see how, in each case, it geometrized interesting physics of entanglement entropies in field theories. And in some cases gave new phenomena. This was one of those where you saw a phase transition, which you don't see in a finite C or a finite in a field theory with a finite number of degrees of freedom. And so there was one stop left on that grand tour, which is 2 separated intervals, which I'm going to do now. And then I'm going to talk about general properties of entropy implied by Ryu Takanagi. And again, there will be the ones that hold in a general field theory or a general quantum system, and then the new ones. And then I'll turn my attention to the covariant holographic entanglement entropy, and we'll see how far I get there. Okay. So far we've only done connected, basically half-line and interval. So the simplest case where you have a disconnected region so is just 2 intervals. And let's call the separation delta. And we have these 2 lengths. And if you recall, in a general field theory, the conclusion was, so now we have this very nice finite quantity, the mutual information, and let's fix, I mean, you can, so what I argued is that in a general CFT, this is a function of the cross ratio, so I could express it fixing any two of these three. Let me fix LA and LB and vary delta, and then what I argued is that it looks like this. It's never 0. It's going to infinity here. I mean, it's going to 0 at delta equals infinity, but it's not equal to 0 at any finite delta. It's going to infinity here. It's decreasing all of those general properties. So let's see what happens holographically. So now we need to find a minimal surface. So as I said before, we know S of A and we know S of B. So the only interesting thing is S of AB. And so we need to find the minimal surface for AB. Using the homology constraint, so keeping track of orientations, let's keep track of orientations for a second. Let me orient these guys. And then we need this to be homologous to AB. So it's going to have to take off like this from here. It's going to have to land somehow. And of course, it starts, I didn't draw it like this, but it starts perpendicularly, as I emphasized before. It has to take off like this, and it has to land like this. And it has to somehow connect these up in geodesics. So I have 4 endpoints, so I guess I'm going to have 2 geodesics. And there's actually only 2 ways to connect these up. So one way is just like this. So this is M1, which is just M of A union M of B. That's always something you can do. So this is an example where it's just handy to keep track of the orientation, because otherwise you might have thought, well, maybe I can connect this point to this point, but you can't, okay? So there's no third surface where they cross or something like that. What's the second one? The second one is, looks like this. And again, these are semicircles in the usual coordinates. And so those are our 2 options, so I'll call this M2. M2 is the union of this and this. Okay? Then it's up to us to calculate the lengths, total length here, and see which one is bigger. Okay? And if we're going to plot, if we choose to plot the mutual information, then we should subtract S of A plus S of B. But S of A plus S of B actually happens to equal the length of M1, as it turns out. So after I do that subtraction, for M1 I get 0, and for M2 I get something else, which is actually a function of delta. And this is what it looks like. So I encourage you to do this calculation. So this is the area of M1 or M2 minus, I didn't give myself enough room. What I'm plotting here is minus actually, let me do it the other way, or I'll make a mistake. Let me just, okay, so we have 2 candidates. So what I'm plotting at first is not actually the mutual information. It'll only be the mutual information once I take the larger of the 2 candidates. Okay, so one candidate is 0. So this is if M1 is the minimal surface as a function of delta. And the other one, when you compute the difference in length between this and this, it looks like this. Now, so recall that this thing is, and recall that we're looking for the minimum of this, so we're looking for the maximum of this between these two options. Okay, so what's the maximum? So here's the maximum. And it is non-negative, which is good. So if we had actually gotten something negative for the mutual information, then that means that something had gone horribly wrong in the calculation. Okay? So so we had these two options, and just for any value of delta, we look at the smaller one because we're looking for the we look for the larger one because we're looking for the smaller value of this, and the larger one does this. Okay? And so now we compare this formula, this picture to this one, and we ask whether Ryu Takenagi has met our expectations, met or exceeded our expectations. So it sort of exceeded them a little bit because indeed it's decreasing. So first of all, indeed it's a function of the cross ratio. Okay, so that's something that, when you actually work out the formula for this, I'm just plotting it as a function of delta, but you can work it out as a function of delta LA and LB, and indeed it's a function of the cross ratio. And that's just because we have a nice ADS geometry here. So it has that the geometry has that conformal symmetry. Indeed, as a function of delta, it's decreasing. Indeed, it's going to infinity as delta goes to 0. But it's doing one thing. Well, it's doing two things that are not happening here. So one thing is that we have a phase transition. And so the same words I said before about phase transition in the gap theory apply here. It must be corrected by some non-perturbative corrections. It must be smoothed out by some non-perturbative corrections. And the other thing it's doing, which is not what we expected, is that it's 0 beyond some critical delta. So this point is at some delta C, which you can work out. This delta C is a function of LA and LB. Yeah?
When you say that the mutual information is monotonic with delta, are you keeping fixed A and B or the L or M?
I'm keeping fixed LA and LB. I'm changing the separation but keeping fixed the lengths of the two intervals. Does that answer your question?
It answers the question, but it leaves me confused because that monotonicity isn't exactly what follows from monotonicity.
Right. So what I said last time is that so that monotonicity follows from a combination of two things. So one is the fact that it's a function of the cross ratio, and the second is a separate argument that it's monotonic for fixed LA and delta as a function of LB, actually monotonically increasing. And that follows from strong subadditivity. And then you combine that with the fact that it's a function of the cross ratio, and you get the fact that for fixed LA and LB, it's a monotonically decreasing function of delta. I didn't go through the details of that argument, but yeah. So here we find this curious feature that it vanishes here. And this is actually not a feature, this is a bug, because I argued before when we just dealt with a general field theory that not only is the mutual information non-negative as it is due to subadditivity, but it's actually positive. Because if it was 0, then that would be saying that the density matrix factorized. So otherwise, if this wasn't true, then you would have this. But this is manifest nonsense because this would imply that the two-point function, the connected two-point function of any operator in A and operator in B would vanish. And certainly that's not true in any field theory. Yes?
So right now we're just keeping track of the leading piece?
Yes, yeah. Don't spoil my punchline here. Yeah. Yeah. So what I've argued here is that this vanishing here is not possible because it would imply that the connected two-point functions vanish, which they certainly don't. But the answer indeed to this conundrum is that here so far we are only keeping track of the leading term, so the order C part. So this is what I plotted here is really the order C part. And so here we have a concrete case where we know for sure that there are order 1 parts and that they're important. Okay, and in fact you can calculate those using what's known about the order 1 part, the order 1 correction to Ryu-Takayanagi, which the important part in this case is simply the bulk mutual information between these two homology regions. So when we're over here, we're in the regime where this is the dominant Ryu-Takayanagi surface. This is the homology region, and this order 1 part of the mutual information is essentially given by the bulk mutual information between those two homology regions. So a contradiction is avoided by order 1 corrections. Okay, those are the examples, and I'll move on to the properties, but are there any questions? Yes?
So what does the critical distance, I guess, tell you? I mean, she said something interesting, that some of the leading effects become these subleading values.
Yeah, so I mean, I can make up some words to go with this phase transition it's a little bit like a deconfinement transition. So, or let's talk about Hawking-Page transition, where you go from a situation at low temperatures where only the collective modes are, so you just have bulk gravitons and other bulk particles, and those are essentially, so those are dual to some single trace operators, so they're essentially representing some collective modes of this. So you have C fields, so you have some ginormous number of fields, but they're only sort of, the temperature is too low for them to be individually active, and then you pass through the Hawking-Page transition and the entropy jumps to being of order C, which means they're now individually active. Maybe a more intuitive picture is the Quark-Gluon Plasma in QCD, where you go from a situation at low temperatures where you just have pions, and then when you raise the temperature enough, then you liberate the quarks and gluons. And so here, presumably, it's something similar where the correlations, because this is a measure of correlation between A and B, at long distances, it's only via collective modes. Only the collective modes are correlated, and so there's an order 1 number of those. And then at short distances, when this is the Ryu-Takayanagi surface, the elementary fields, of which there are C of them, are actually sort of carrying the correlation. So that's at least, I mean, I don't actually have independent evidence other than this particular calculation for that story, but I think it's sort of fits with what we know. I think it would actually be very interesting to sort of be more specific about that story. Yeah.
When you say this is similar to confinement deconfinement phase transition, does the separation in some way mark the temperature reduction?
So no, I didn't mean that literally. That here, what I'm talking about is not which. So even here, if you look at row AB, if you look at even row A or row B or row AB, the entropy is order C. It's only in the difference between this and this that you lose that order C part. So certainly the individual fields are already quote unquote deconfined simply because we have high temperature near the entangling surface in terms of this modular Hamiltonian that Tom showed us. So everybody's deconfined, but they're not correlated with each other. The correlations here are only being carried by the collective modes. Okay, you can think of like, if you have gas in a box separated by a piston, you have, at some temperature, the gas has a very large entropy on both sides of the piston, but if you look at how the two gases are correlated with each other, they're only talking to each other via this collective mode, which is the position of the piston. And that thing is fluctuating, its fluctuations are down by 1 over the square root of the number of gas molecules on the two sides. Okay? Any other questions? Yes?
So, in order not to have the third possibility, do you demand that the two intervals have the same orientation?
Well, they do have the same orientation because the orientation of any boundary region is inherited from the whole boundary hasn't, we assign an orientation to the whole boundary. Yeah. I mean, you could ask the question, nothing stops me from calculating the length of this thing and asking, does that signify something? So I have no idea. It doesn't signify anything that I know, but yeah. Yeah.
Just from this diagram on the right, what can you conclude about the C function?
So the C function.
Is there something funny happening at that point where it touches the x-axis, the delta, delta 2 or something, delta critical or something that you wrote?
The C function is calculated from the entropy of a single interval as a function of its length.
Right.
So you don't directly learn anything about the C function from this calculation. You learn something from the calculations I did before for a single interval as a function of length. And you can certainly derive the C function there.
What I want to say is that if you are talking about phase transitions, then the C function should capture the sudden drop of the degrees of freedom in the system.
Yeah, so that's getting back to, that's in the gapped case. I assume Tom is going to cover the C theorem, but basically the C function, for those of you who don't, is essentially this. And so indeed, it's going to, in the holographic case, it looks rather funny because it does this. It's certainly monotonic, but yeah. Yeah?
How do the geodesic shapes change due to the O1 correction?
So at first order, they don't move because they were already minima. And another thing, let me leave it at that. I'm not sure. The other thing about this particular case is we have so much symmetry that they are actually, at least if you're looking at a single interval, it's in any case determined by the symmetry. Now that symmetry is broken when you have multiple intervals, so I suppose at higher orders in G Newton they probably do move, but I don't know how they move. That seems like a hard problem, yeah.
But can you relate, even if there's opposite calculations, you might be able to relate that delta C to where that chop off is, just because how you had mentioned like the qubits of the edge are only correlated with a certain length within, I don't know, and this is telling you that at some point they're separate and they're not.
Yeah, I agree that of course this was done in a gap theory, so clearly some similar phenomenon is going on, and there might be some, let me not, it sounds, what you're saying sounds interesting. I encourage you to pursue it, but it would,
I just want to follow up the question about this, first of all, the question about this minimal surface. So, if I only take the essay class, then it's, I'm talking about the statistical average of the geodesic, right? So, but that would be different from if I average of SAD, because that would be coherent. That would be variance between the two
Yeah, I didn't say that they wouldn't move at higher orders in G. I mean, I think they probably will move at higher orders in G Newton. But then I mean, past order 1. At order 1, they don't move because they were already minima. And the position of a minimum to first order, if you perturb the geometry, doesn't move to first order. Once you get higher than first order, then you have to deal with, interactions, and it's.
You mean to say they do move at first order corrections, but doesn't affect their entropy?
Yeah, that's what I meant to say. Thank you. Okay, they will move at first order, but because they're minimal surfaces, that doesn't change their area to first order. Their area doesn't change to first order due to their movement. Okay. Let me move on to. So far we've done examples, and now I want to move on to general properties. And again, the lesson is always the same, that it geometrizes things we know and love about entanglement entropies in general in a very simple and beautiful way, but also goes beyond that and has some special properties. Well, we've already seen some properties, actually. So one of them that I've already argued is that if rho is pure, then S of A complement equals S of A. And I already gave the argument for that. Another one that I've implicitly given here is for subadditivity. And I did it just for this special case, but you can see that the argument is pretty general, which is, well, subadditivity is this statement. And the reason that it obeys this automatically is simply that one locally minimal surface is always M of A union M of B, and therefore the true minimal surface can't have area more than that of M of A union M of B, which is S of A plus S of B. Very simple. And then this argument can be strengthened to give a proof of strong subadditivity. And it's rather remarkable how effortlessly RT satisfies strong subadditivity, given how, as Edward emphasized, subtle and difficult it is to prove strong subadditivity for a general quantum system. I mean, in the proof I'm going to give, it has almost no ingredients. For example, I'm not going to use the Einstein equation. I'm just going to assume that there's some geometry and that the entropies are computed by areas of minimal surfaces homologous to boundary regions. And that's it. The geometry could be anything. It doesn't have to be asymptotically as far as this proof is concerned, it doesn't even have to be asymptotically hyperbolic or anything. It's actually a little bit surprising. So now we're interested. So let me just state the inequality here. Oh, I just remembered I wanted to say something about this. What's on this board? This is a special case of Iraqi-Lieb. Iraqi-Lieb says this. So you see that if S total is 0, then that implies that these are equal. And this is not really a different inequality from subadditivity. Iraqi-Lieb is just what you get, and I think Edward might have said this, by adding a purifying state. So if I purify AB, and then I trace out A, then I get, so if I add a purifying system C to AB, and I trace out A, I get an inequality for BC, which is a Iraqi-Lieb. And so as long as if your mixed state holographically is a black hole, then you can, is a thermal state which is represented by a black hole, then you can purify that holographically by going to this extended geometry. And so actually, this is actually, if you use that trick, is actually a special case of this. So in other words, what I'm saying is that the purification trick, which is very handy for relating different properties in quantum information theory, can be applied holographically, because the kinds of mixed states we usually deal with are, can be purified holographically. Okay, so let me get back to this. So now we have 3 regions, and the proof I'll give is totally general, but I'll just give the cartoon version where I've decided strategically to line up my, first of all, to draw it in 1 dimension. That's the limitation of my drawing abilities. And to line them up, ABC. And then we're interested, first of all, in the left-hand side. So we find the minimal surface for AB. And then we find the minimal surface for BC. Okay? And I'm not actually that only interested in the minimal surfaces. I'm also interested in the homology regions. And what I can do is I can look at the union and the intersection of the respective homology regions. So I define a region, R tilde of B, the name hopefully will be clear in a second, as the intersection of these 2 homology regions. And a region I'll call R tilde of ABC as their union. Okay, so this is R tilde of B, and R tilde of ABC is this whole thing. And then what you can see, and what you can show more generally, is that, well, so first of all, what I want to say is that R tilde of B has a boundary. And so that boundary, I'm going to call M tilde of B. And R tilde of ABC has a boundary, which I'll call M tilde of ABC. Okay? And then, of course, by construction, M tilde of B is homologous to B, because here's the homology region. And of course, I've used the fact that on the boundary, the intersection of AB and BC is B, so that the boundary, so a region has a boundary and a bulk boundary. The boundary of R tilde of B is B, and the boundary of R tilde of ABC is ABC. Okay, so I've constructed 2 surfaces which are homologous respectively to B and to ABC in the bulk. And then what you can show, and it's pretty clear from the picture, but you can show it more generally, is that the total area of this and this equals the total area of this and this. So area of B. Actually, this is not quite true. It can, if you think about it a little bit more, there can be sort of isolated pieces where there's sort of extra pieces that appear if some of the, if the AB and the BC RT surfaces kind of coincide, if they don't cross transversely, then you get extra pieces in this. But I'm going to leave that detail off because, trust me, they contribute to the inequality in the right direction, so they don't ruin the inequality. If you want the details, I wrote a paper called General Properties of Holographic Entanglement Entropy, and that's all written out in there. Okay, so let's ignore that case and proceed. And now, what do we have here? Well, so far, it seems like we don't have too much because, after all, nobody said, and it's not usually true anyway, that this is the minimal surface. So what does this tell us? What we wanted, so here, of course, the right-hand side, we have this. But the left-hand side seems not too useful because these aren't the minimal surfaces for B and ABC, which is what we really wanted there. And that's true, but of course, the minimal surfaces, obviously by definition, have an area that's no larger than this and this. So I should have anticipated needing to write a line above here. So sorry, I have to squeeze this in. And on this slide, I've set 4G Newton equal to 1. Okay. Okay, that's the proof, very easy. And so the fact that RT automatically obeys strong subadditivity is, was sort of one of the, besides these special cases I gave you where it matches what we knew to be true in the field theory, like the area law divergence and so on, the fact that it automatically satisfies such a non-trivial property was sort of one of the things that made people really believe that the formula is correct. Yeah? Yeah, these are not smooth. The M tildes are not smooth. Yeah, when I said the minimal surface, I didn't put a restriction that the surfaces had to be smooth that we minimized over, but in any case, it wouldn't have mattered because this one can be obtained as a limit of smooth ones, if you're worried about that. So I can smooth them out without changing the area. So, yeah. Right, so it usually is strict, but you can find, so in this case it's strict, but you can cook up cases where it's saturated. And if you want to see, in this paper that I mentioned, I write the most general case where it's saturated. I mean, basically, if the things kind of coincide, if they're not crossing each other transversely, then, and if they just sort of have these disconnected pieces that coincide, then it'll be saturated. So in this cartoon, it's strict, but any other questions? Okay, this is famously a general property of entanglement entropy, but RT does things that are not necessarily general properties because we're dealing with a very special kind of state, namely holographic states. And actually, it's very interesting to ask, to use entanglement entropies to study special properties because we don't really understand in any kind of very general way what kinds of states holographic states are. The first property that is true for all holographic states but not true for all quantum states is the one I'll do next, which is superadditivity of mutual information. And unfortunately, in the literature, It's also goes by this name, monogamy of mutual information, which there's some obscure reason for that that would take me too long to explain. So, so this is often just called MMI. And it's proved the same way. It's also for 3 regions. And the proof is just more complicated, but with exactly the same ingredients. And I'm not going to go through that argument. But here's the inequality. It's actually more symmetric than strong subadditivity. And maybe it's not too meaningful when you look at this inequality, what's going on. So let me rewrite it in terms of the mutual information. Let me actually remind you what this inequality looks like in terms of the mutual information. This is monotonicity of mutual information. And this one is superadditivity of the mutual information, meaning that with respect to holding one of the arguments fixed, it's superadditive with respect to the other one. These are the same inequality. Okay? Let me just give you an example. So, to kind of maybe motivate why something like this might be true holographically. So we learned before from this that the mutual information, if 2 intervals are sufficiently far apart relative to their sizes, is 0. And so we can easily cook up a situation where you're on one side of the phase transition for these 2, but on the other side for this. So what I mean is, like, fix an A, and then let's put B and C next to each other in such a way that when you calculate I of A, B, C, because BC is obviously, larger than either B or C, this thing is non-zero, but I of A with B is 0 and I of A with C is 0. I leave it as an exercise to actually, construct such a configuration. It's not hard. And so in this case, obviously you can get 0 on the right-hand side, something non-zero on the left-hand side. Of course, that's not a proof that it's always true holographically, but it's just, you can see what's going on holographically that, so if we didn't have a holographic theory, and in fact, this inequality can be violated in non-holographic field theory. So free fermion does not obey, so like I think the statement is that a massless free fermion actually always saturates this inequality, but a massive free fermion can violate it or satisfy it depending on the particular arrangement of the intervals. And in any case, it's clear that if you have this kind of curve, then it just kind of depends on the shape of the curve whether you're going to obey it or not for a configuration like this. Okay? And let me just quickly convince you that this inequality doesn't hold for a general quantum state. In fact, it doesn't even hold for a general classical state. And it's, pretty much almost the simplest kind of state you could write down already violates it, which is just, a fancy way to say it would be the 4-party GHZ state. But let me just, so if I have 3 qubits, and it's 50% up, 50% 0, 0, 0, 50% 1, 1, 1. So this is actually a perfectly classical state. And you can calculate these things and see that it's violated.
It's violated whenever SAC is less than SA plus SC, right?
Whenever SAC is less than SA plus SC, SAC is always less than or equal to SA plus SC.
Oh, wait. I'm confused, because if I remove those terms, I just have some strong subadditivity.
Right, but the way the inequality goes is that it's stronger than, if you assume subadditivity, it's stronger than strong subadditivity. I'm not going to try to work, I'll definitely get it wrong if I try to work out the inequalities in real time, but I mean, you can see it from here that right, if I assume if I give myself subadditivity, I think I can operate at that level of doing algebra on the board in front of 100 people. Okay, I'm done with RT, so time for any questions about that. Yeah?
Is it known if subleading corrections to RT maintain strong subadditivity?
Well, they better. I think that it follows, like the order 1, I think it's pretty clear that the order 1 corrections, at least the ones that are given by the bulk entanglement entropy, obey it. Because on the assumption that the bulk fields obey strong subadditivity. I'm not sure to what extent it's been shown for all these other terms that you get. Yeah?
Can you maybe ask a more general question, like what kind of functions obey all these properties? And like, is a minimal area function the unique one?
It's a good question. So I mean, it's certainly not unique if you give yourself in your choice of function other geometric invariants. Because as I said, once you add, for example, alpha prime corrections, then you get new terms that you're minimizing, just like Aaron discussed with the black hole entropy, sort of walled-like corrections to the, and those had better also obey strong subadditivity and so on. Probably an argument could be made if, yeah, I mean, I'm not sure. You have to decide on some beginning assumptions about what type of function you're allowing yourself, but I can imagine some useful theorem of that kind.
You can at least worry about the places where you reconnect, whether there's dependence on things like extrinsic curvature, you might get weird delta function transductions.
Yeah, and something that's interesting about that is for this particular Gauss-Bonnet case is that basically, you're going to be, this argument is going to be fine as long as the function that you're minimizing is extensive, meaning that if you glue two surfaces together, then it's the sum of what you have for the two sides. And that's a true fact about the Einstein-Hilbert Lagrangian as long as you add the Gibbons-Hawking-York boundary term. And therefore, for the Gauss-Bonnet corrections, where the correction you add is essentially an Einstein-Hilbert term on the surface, it's automatically okay. Even with these, even though you develop extra terms at the intersection. But for something else, I think it's more something one has to check.
You also want to be positive, obviously.
You want, well, but it's going to be positive because assuming you always work perturbatively in your correction that you add. I don't think we want to take too seriously this, I don't think we want to add this extra term with a finite coefficient. I think we will always want to add it with an infinitesimal coefficient, so it can't make it negative. Yeah?
Besides direct calculations in CFT, is there any other ways that fixes the coefficient of forces in RT formula? Because the fact that RT formula always is inequality certainly does not give us the coefficient.
Yeah, that's like, Bekenstein's argument or the laws of black hole thermodynamics didn't fix the coefficient.
But then we have the temperature.
Yeah, so somewhere you need a calibration system. And the calibration system, in this case, I would say the simplest one is the black hole, where you then go back to Bekenstein-Hawking. You know, but anything where you can compute it in a CFT, for example, a single interval will calibrate. But of course, a single interval is a black hole in a different coordinate system. So that's actually the same. Yeah.
For the mutual information, is there any general method to calculate the order 1 correction?
Well, yeah, so the order 1 corrections are known, to RT are known. So you just apply, oh, you meant, I guess I didn't quite understand the point of the question. You meant how do I compute the bulk mutual information?
Yes, the bulk correction to correct the mutual information.
So, I mean, the question was how you actually, in practice, compute this mutual information in the bulk between the two homology regions. And there are certainly techniques. Basically, you do a replica trick in the bulk. And so this is a paper that Tom and César Agon wrote that where they actually calculated this and compared it to the field theory result. So, I mean, it's not easy to do those calculations, but yeah.
So how many of these inequalities hold for other intelligent space?
For how many hold for what? Oh, so this is what I was saying. I mean, it's actually a little bit disturbing how general this argument is. That this argument goes through for any geometry. I mean, it's so simple that it requires knowing nothing about the actual geometry. So in that sense, it's not very helpful for constraining, like if somebody has some Lifshitz or Schrodinger or non-commutative or something, and they apply Ryutakyanagi, it's going to work in this sense. It's going to obey this constraint. Whether that means their calculation is correct or not is a different story, but this is not helpful at all in constraining, you know, or TT bar or something. I mean, in constraining, you know, legitimate holographic dualities. This is not true when we go to the covariant. The covariant one is much more useful in that sense. Sure. Why not? I mean, of course, you need to cut it off just like you need to cut this off. Other questions? Okay. Okay, so my next and last topic, and I'm not going to get super far into it, is the covariant version. So these lectures are going to end in an outline of things I wanted to say but don't have time to. Okay, so so far we've been restricting to a time reversal invariant slice. I do want to say that restriction is actually not so terrible in practice because, you know, at least 90% of the time we're interested in static states, and those are automatically time reversal invariant. But of course, it's not always true. I mean, if you're studying some quench or something, then you need to know what happens in a time-dependent spacetime. Some black hole collapse doesn't have any time reversal symmetry, and so certainly RT should, if RT is for real, it should have a generalization to those cases, which, from the point of view of holography and general relativity, are just as good spacetimes as any one that happens to have a time reversal symmetry. And another thing is that even if you have a static spacetime, you might be interested in the entanglement entropy of a region which is not lying on a constant time slice, which is boosted relative to the natural time coordinate. And so again, RT is useless for that. So that's not good. Now, you could say, well, just forget the restriction of keeping your minimal surface on a constant time slice. Just why not just say, so assuming we keep this part of the formula, and then we're just trying to figure out what we should choose for this, what, you know, why not just say it's the minimal surface in the bulk that's homologous to A? Well, I think Edward actually already answered that when he talked about the fact that space-like geodesics are not either minima or maxima of the length, and the same thing holds in general. By the way, for surface, I always mean, for me, a surface is codimension 2 with respect to space-time, space-like submanifold. So just like with a space-like geodesic, you can always decrease the area by wiggling it up and down in the time direction. So these things don't even exist in a Lorentzian manifold. So that's no good. We're going to have to control, we're going to have to, at the very least, if we're going to make something work like this, we're going to have to control the wiggling in the time direction. So there are two ways you could try to generalize RT, which I think are pretty natural. And the first one is to say, well, to fix the problem of wiggles in the time direction. Well, there are many things you could think of. Okay, I mean, you could say, well, I need a canonical slice. Let me look at a maximal volume slice or something like that. There's many things you could think of. So I've selected two, for good reason. So the first is to say, well, let me rewrite how I wrote the RT formula slightly. With the RT formula, I just said it's the globally minimal surface, but let me rewrite that as among the locally minimal surfaces, the one with the least area, which is obviously the same. And the reason for doing that, for making it more complicated in that way, is that the notion of a locally minimal surface has a nice generalization, which is locally minimal just means that the trace of the extrinsic curvature is 0. Okay, and that I can generalize. Okay, so I say M of A is an extremal surface homologous to A, and if there's more than one, so the one with least area. So I do the minimization over area as a second step after forcing it to be extremal. Extremal means that the trace of the extrinsic curvature is 0. So there are a few ways to say it. So one is that G mu nu K mu nu A equals 0. This is a normal index. So the extrinsic curvature tensor for the extrinsic curvature you might normally think of for a hypersurface as having two indices which are in the tangent space to the hypersurface. If you have something which is higher codimension, it grows an index which is a normal index in addition to the two tangent indices. And here I'm just taking the trace over the tangent indices and asking for that to be 0. So this is two equations because I'm in codimension 2, so there's two values of this. This is the same as saying that both, or let me give a simpler one. It's an extremum of the area. So in other words, I say forget minimum and maximum because we've already decided that doesn't work, but just it's a local extremum of the area. So to first order variations in the surface don't change the area. And a third one is that if you look at the expansions in the two null directions, so since it's codimension 2, there are two null directions that are orthogonal to the surface. And so the expansions of congruence of null geodesics in both of those directions are 0. Let me just say, in both directions. Well, there's really 4 directions. I can send out null geodesics from a given codimension to space-like surface, to the future and the past, and then to the left and to the right. But of course, the expansion in this direction is minus the expansion here, and similarly here, so I just have to fix 2 of them to be 0. Then the other 2 will be 0. Okay, so this notion of an extremal surface is super handy. It's basically the natural generalization of a space-like geodesic. And in fact, if the bulk is 3-dimensional, then an extremal surface is a space-like geodesic. Say that. So okay. So that's proposal 1. Oh, and it has a name. It was put forth by Hubini, Rangamani, and Takeyanagi, so it's called HRT. Okay. Proposal 2 was put forth by Aaron, but he made the mistake of giving it a snappy name, which is Maximin. So the lesson is, if you want people to call your great discovery by your name, don't give it a snappy name. So people call it Maximin. And it's like this. Sorry. Yeah, I wanted to say one thing before I get to Maximin, which is that we should always refer back to our canonical example of the black hole to make sure we're at least getting that case right, for where we take a whole boundary as our as our region A. And so what I just wanted to say is that indeed the bifurcation surface, and I think Aaron said this, is extremal. So this is a sphere. It's a codimension 2 sphere. And indeed, the expansions are 0. The expansion going out this way is 0, and this way is 0. Okay, so indeed, this formula does isolate. In fact, it's the only extremal surface which is homologous to a time slice of one entire boundary. So, for example, if you look at spheres, they have radius r in the usual coordinates, and r is increasing out to the boundary, decreasing up to the singularity and down to this singularity, and so this is a saddle point of r. And so at least as far as those variations are concerned, it's extremal. And so indeed, the HRT is getting the right answer in this case. Okay. So back to Maximin. So the second way to cure this problem is to say, well, obviously the problem is that this codimension 2 surface is it might be that, if we wiggle it in the time direction, it decreases the area. So let's ask for the maximum with respect to variations in the time direction, but the minimum with respect to variations in the space direction. In other words, we explicitly factorize the problem into variations in the space direction, and we want those it to be a minimum with respect to those, but a maximum with respect to variations in the time direction. So you might say, well, how do we covariantly split up space and time? So the proposal is very clever that way. And that's why it's called maximin. So we maximize, so first of all, pick a Cauchy slice of the bulk and look for the minimal area surface in that Cauchy slice. So sigma is a bulk Cauchy slice of the area. So for a given sigma, and we require sigma to contain the entangling surface. So let me draw a picture. And we're going to consider, so the entangling surface is here. And we require sigma to pass through the entangling surface. So it's going to do something and then go out into the bulk. And this is sigma. Okay? So for a given sigma, we solve that problem. Find the minimal area surface. And then we say, well, in terms of variations of sigma, so variations of sigma are allowing this surface to wiggle up and down in the time direction. And so with respect to those variations, we want to maximize. And this is supposed to be S of A with the usual. Okay, and let's again go back to this thing. And you can actually see by what I said before. So if we consider all these different slices, so let me just give a few examples of slices. These are all bulk Cauchy slices. There's a lot of other bulk Cauchy slices you can draw. And on each one, you can find the minimum. So for example, on this one, the minimum will be somewhere here. So these are like going through, they look like wormhole geometries. The geometry on one of these, in fact, it looks like some very long wormhole. And it has a minimal surface somewhere in the middle. And so then as a function of which sigma you pick, if you look at the minimal surface area, it looks like this. It goes up and then down. And the maximum, of course, is at the bifurcation horizon for the reason that I gave before, that R is decreasing in these directions and increasing in these directions. Okay, so again, you land where you wanted to land. Okay. Is there a question? Yes? Well, there's not, oh yeah, one thing I should have said is that a nice thing about spacetimes that have a time reversal symmetry is that they have a nice real Euclidean continuation. And then you can use all kinds of Euclidean quantum gravity in that real Euclidean continuation. If it doesn't, then it doesn't. Well, if it has some symmetry, it may have some complex Euclidean continuation, but if it's just some random space-time, it doesn't really have any natural continuation. And so we can't really just fall back on working in a Euclidean space. Yeah, you might have said, oh, we're going to work in the Euclidean space where we don't have this problem. Not sure if that was what you had in mind, but. Well, a Wick rotation assumes some analyticity, right? I mean, it assumes basically that the functions are analytic, the metric coefficients are analytic functions of the coordinates.
Also, if you want the Euclidean metric to be real, you want the moment of time to
Right, so that's what I said before, that if you have a moment of time symmetry, then not only are the, and it's analytic, I mean, I didn't emphasize that before, then after you do the Wick rotation, you end up with a geometry that's still real. It could be analytic but not have a moment of time symmetry, and then there is a natural Wick rotation, but it's complex. Like Kerr, for example, and then you can argue about how meaningful that is or whatever. But it's not particularly easy to work with geometrically. Okay, so now we have on the board these two proposals, and is either one right? And if so, which one? Well, here's the great thing. You don't have to decide. I could have taken a vote, but you don't have to decide because they're actually the same. And that's a very nice fact. And let me give a flavor of that argument. So, and in fact, we're going to get a very nice bonus out of that argument. Oh, so this is nice for a bunch of reasons. Not only because it means that you don't have to make up your mind which one you like better, or who you like better, but also because they kind of look different, and so that's great. If they were trivially equal, you know, it wouldn't be so interesting. But therefore they're useful for different things, and in particular, as a kind of general vague rule. This one is more useful for doing calculations, and this one is more useful for proving theorems and deriving properties. So, for example, if you actually want to find this entropy, let's say you have a three-dimensional bulk, then as I said, the extremal surface is a space like geodesic. And space like geodesics are really, really easy to find. Now, in higher dimensions, it's actually not so easy to solve the extremal surface equation. It's some weird kind of PDE that's like wrong signature. So it's not hyperbolic, it's not elliptic. On the other hand, with Maximin, because you can, you're at least dealing with. So, for example, in the proof of strong subadditivity, you know, obviously it was crucial that we were minimizing something. And here we're not, it's more complicated, but at least at one step we're minimizing, at another step we're maximizing, so maybe if we're clever enough, you know, we'll be able to prove something, okay? To give a flavor of that, let me sketch out this proof. So there are two steps. The first step, and an example of something that it's much easier to prove with Maximin than with HRT is this. And then the second step is that any Maximin surface is HRT. And that establishes that they're equivalent, but it establishes more than that because it establishes that there exists an HRT surface. And let me just say a few words that, you know, with RT, I never even raised the question of whether there exists a minimal surface. And the reason is because it's kind of obvious that there exists a minimal surface. Of course, it's obvious it's in the category of statements that are very obviously true and therefore incredibly difficult to prove, right? I mean, so mathematicians have spent entire careers, I mean, there's an entire branch of mathematics called geometric measure theory, which is just like proving existence of minimal surfaces, and people have gotten Fields medals and stuff for that. But it's the kind of math that physicists generally sweep under the rug and say, well, it's obvious, so I'm not going to think about it anymore. But then when it's like, and the reason it's obvious is that, you know, if you, it is essentially, this is one of these horrible arguments, but is essentially that the area functional is bounded below, right? And so the argument is that any function which is bounded below has a minimum, which is of course total BS. But now, what about the extremal thing? We weren't minimizing or maximizing anything. I don't know, do there exist solutions to this weird PDE? I mean, I can believe that there exists a space like, I mean, even in 3 dimensions, does there necessarily exist a space like PDE, a space like geodesic connecting any boundary point to any other boundary point, or any boundary point to any other boundary point which is space-like related on the boundary? That's not an obvious theorem. When you go to higher dimensions, it's really not obvious that there exists an extremal surface with the correct boundary conditions, okay? But I think it's, first of all, the existence of a minimal surface within a given Cauchy slice we can put into that category of obvious. Now you have to worry, is there a maximum as I vary the Cauchy slice? And here, it's maybe less obvious, but it's kind of believable because we know that if you make your Cauchy slice wiggle too much or go too much up into the future, it's going to make the minimum, like let's say I do some Cauchy slice which is going way up in time and way down, then there's going to be a minimal, the metric on that thing is very small because the surface is almost null. The induced metric on it is small, and so the minimal surface is going to be very, very small. And so you don't have to really worry about that case because here we're maximizing. And so it's at least intuitively clear that, you know, there should exist a maximum. Okay? Now, that's not to say that proving step 1 is trivial. It's not, but at least you have the tools to attack the problem. Okay? You start pulling in theorems about, you know, you have to prove kind of compactness of the space of slices and stuff like that. And I'm not going to go through that proof. It's a bit technical, but at least you have the tools to start. What I am going to talk about is this step. So let me write. Okay. So here, for part 2, there are 2 parts, 2 subparts. The first is that a maximin surface is extremal. That's hopefully sort of intuitively clear from what I've said, that basically you have all the degrees of freedom for varying your surface. You can vary it in the space direction or the time direction. If you want to vary it in the time direction, you vary sigma. And so therefore, all variations are present and accounted for. And this is saying that again, the variations in the spatial direction it's an extremum with respect to this, and this is saying it's an extremum with respect to the ones in the time direction. Okay, I'm not going to, you can obviously write those words in equations. I'm going to take that as sort of intuitively clear. And then the second step is, but the question that this leaves open is whether you could so you could have multiple extremal surfaces. The maximin one is one of the extremal ones, but maybe some other extremal surface has a smaller area and is the HRT surface, and then they would be different. So that's what we want to rule out. Okay? So this part is any other extremal surface. Let's call it M1. So let me call this M0. So I'm calling the maximin surface M0, and some other extremal surface M1 has a larger area, or at least as big. Okay? And again, I'm not going to cross all the T's and dot all the I's here. I'm just going to sketch out how this works. So I have my A, and then we have to keep track of D of A. And I have some M1, which I'm just drawing as a point, so there's some extra dimensions this way. And so there's a lemma here, which I'm not going to prove, but if you have an extremal surface, so first of all, we're talking about extremal surface is homologous to A, so there's some R1 that connects M1 to A, and I can ask about its domain of dependence. And its domain of dependence, it turns out, looks like this. So this here is D of R1. And when I say it looks like this, what I mean is that it intersects the boundary on D of A. So D of R1 intersects the boundary on D of A. Meantime, we have our Maximin surface, which is somewhere else. And is sitting on some Cauchy slice. So here's M0. It's sitting on some Cauchy slice, sigma naught. That's the Maximin slice, the one that's maximizing here. Oh, it doesn't have to end, sorry. It doesn't have to end on A, but it has to intersect, I mean, it has to pass through the entangling surface, okay? So let me draw it, what this plane looks like. So here I have A, I have D of A, and then I have sigma naught. This is sigma naught intersect the boundary. Okay, on some it intersects the boundary on some Cauchy slice and it passes through the entangling surface. Okay, so now if I look at the intersection of sigma naught with D of R1, so this space-time region, I get this part of the Maximin slice. And the existence of this part guarantees that this intersection here with this, it turns out it doesn't look null, but this is actually a null surface, a null hypersurface. This is some codimension 2 space-like surface, which I've shown is homologous to A. Okay? Or more precisely, what it's homologous to is the intersection of sigma naught with the causal domain of A. Okay, so, and I'm going to call that M2. So the important statement here is that M2 is homologous to the intersection of sigma naught with D of A. Yeah, I didn't write the homology condition here on M, but it's that. The homology condition here, M is contained in sigma, and M is homologous to the intersection of sigma with D of A. That's the homology condition in Maximin. Great. So that means by the minimization, so M2 is homologous, is in the right homology class, and therefore it has area at least as large as that of M0. Okay, so we get one inequality just from the definition. So definition of Maximin implies that the area of M2 is at least as big as the area of M0. But that's not what we wanted to show. What we wanted to show was this. So we need some way of relating M1 to M2. Yes?
Is that defined as the intersection of sigma naught and p of R1 or p of A?
It's homologous to this. This is codimension 2. It's codimension 1 on the boundary. It's codimension 2 with respect to the bulk. So in other words, this thing here, let me show you where it is on this diagram. It's here. So I'm saying this is homologous to this via this. This is this homology region here. Okay, so how do you know, maybe this has a tiny area. How do you know that it, I mean, clearly what I'm going to prove next is that this area is at least as big as this, right? Well, for that, we use this fact about extremal surfaces. Remember, this is defined as an extremal surface. And an extremal surface has vanishing expansion in all 4 directions. And therefore, the boundary, I think that this is something that Edward showed us, that, but in any case it's true, that the boundary of this region is made up of null geodesics sent out orthogonally from M1. Those null geodesics have initial expansion 0. And now, and this is important, so now I'm actually going to invoke a condition on the spacetime, namely the null energy condition. So this is okay, and of course a very interesting set of questions is around relaxing this assumption. But so if we assume the null energy condition plus the Einstein equation plus the Ray-Chadori equation, and this style of argument we've already seen, so I don't have to repeat it, implies theta dot is negative, or at least is non-positive. And since theta is 0 initially, this implies that theta is non-positive. And this implies that the area of M2 is greater than or equal to the area of M1. Okay, so on this piece, we follow the null geodesics and we use the Ray-Chadori equation and the null energy condition. On this piece, we use the definition of maximin, and that's how we establish a bound relating this to this. Okay? Now, this style of argument is all over this subject. So since I'm out of time, I will just list the things that I'm not going to tell you. So actually, so I'll leave these as exercises. So the first thing I wanted to tell you to prove, actually the first one I think is a pretty reasonable exercise. I've already given you all the ingredients. And it's something that people usually take for granted. I'm sure it's written down somewhere. The statement that HRT implies RT. In other words, that if I have a time reflection invariant, if I have a time reflection symmetry and I consider a region which is on the invariant slice, then my HRT surface is my RT surface. And part of that is obvious, that the RT surface is extremal. But the question is, maybe in some general spacetime, there's some other extremal surface which is smaller, which is not on the time reflection symmetric slice, and which actually has a smaller area. And you can rule that out by this same kind of argument. Slightly harder, but once you have the tools, you can do also is that this obeys strong subadditivity. The proof we had before doesn't apply now. I mean, one way to see it is that there's no particular reason, and it's not usually true, that these M of AB and M of BC lie on the same slice. Here you do need one lemma which is not particularly easy to prove, which is that, which is kind of in this, a stronger version of this, that there exists a common maximum slice for nested regions, and in particular that B and ABC have a common maximum slice. In other words, there's a single slice where that their maximum surfaces or their HRT surfaces both live on. And another one is that HRT obeys boundary causality, which is essentially a stronger version of the Galois-Wald theorem, which is that if you change the boundary Hamiltonian, if I do a perturbation to the boundary Hamiltonian inside the domain of dependence of A, it should not be able to change the entanglement entropy of A. And so to see whether HRT actually obeys this, you have to see what happens to the signals sent from within this and whether they can actually hit the region that the extremal surface is in. If they can, then they could change its area. That would be bad. Okay, so this is like Galois-Wald, but instead of sending a signal from one boundary point to another boundary point, we're trying to send a signal from a boundary point to something in the interior of the bulk, and showing that that's not possible. On the other hand, you can send a signal from here to the HRT surface. So by changing the boundary Hamiltonian at this point, as long as it's actually outside also the domain of a complement, you can actually change the entanglement entropy. And the last thing that I'm not going to tell you about is that, because, we discussed it before briefly, in a black hole formed from collapsed, S of A complement equals S of A. In other words, so more generally, HRT is telling you a fine-grained entropy, not a coarse-grained entropy. So it's telling you the entropy of the density matrix that is unitarily evolving on the boundary without any coarse graining. So if you have a black hole which is formed from collapse and you wait 1 million years and you compute the entropies, I mean, there are two ways to do it. You can do it with the sort of thermodynamic coarse-grained density matrix, but that's not what HRT will give you. HRT will give you the answer you get with respect to the unitarily evolved pure density matrix that you started with 1 million years ago. Okay? So this you can also show. And that's it. I'm way over time. Thank you.